We're going to learn about variance and covariance of random variables. Just like in Chapter 1, the mean, or in this case the expected value of a random variable x, is of special importance in statistics because it describes where the probability distribution is centered. By itself, however, the mean does not give an adequate description of the shape of the distribution. We also need to characterize the variability in the distribution. The most important measure of variability of a random variable, big X, is obtained by the quantity which is referred to as the variance of the random variable x, or the variance of the probability distribution of x, and this is denoted by var x, or the symbol sigma x squared, or simply we can denote it by sigma square. And so what we want to do is let's let x be a random variable with probability distribution f of x and mean mu. The variance of x is, we'll do discrete first, sigma square is equal to the expected value of x minus mu square. And this is equal to, because it's discrete, we will do summation. It's equal to the sum of x minus mu square times f of x. And then for continuous, it's integration instead of summation. So we will do sigma square is equal to the expected value of x minus mu square is equal to the integration of minus infinity to infinity of x minus mu square times f of x dx. The positive square root of the variance, sigma, is called the standard deviation. We're going to look at an example. It is a discrete example. We have two companies, Company A and Company B, and we're going to let the random variable x represent the number of automobiles that are used for official business purposes on any given work day. The probability distribution for Company A is the x is 1, 2, and 3, and the f of x is 0.3, 0.4, and 0.3. And then for Company B, we're going to go from x equals 0 to 4 to f of x from 0.2 to 0.1. So 0 is with 0.2, 1 with 0.1, and so on. And we want to find the variances for Company A and Company B and compare. So we're going to start with Company A, and we're going to find mu A, or the expected value of x. So we look at each x times f of x and sum them. So we have 1 times 0.3 plus 2 times 0.4 plus 3 times 0.3 is equal to mu of A of 2.0. And then we're going to find the variance of A, sigma square A, and that is equal to the sum of x from 1 to 3 and of x minus 2 square. And 2 is the mu. And so we are then going to take each value of x and plug it in and square it. So we'll take 1 minus 2 square times the f of x of 1 is 0.3, so that's times 0.3, plus 2 minus 2 square times 0.4, since that's the f of x of 2, plus 3 minus 2 square times 0.3, And when we do the summation, our variance is equal to 0.6. Okay, and now we're going to do company B. So we're going to do the same thing. We're going to find mu of B, which is the expected value of x. And so we're going to take each value of x multiplied by its f of x and sum them. So for 0, it's times 0.2 for company B, plus 1 times 0.1, plus 2 times 0.3, plus 3 times 0.3, plus 4 times 0.1. And what we will see is the mean is equal to 2.0. So the mu is 2.0. We now need to find our variance of B, which is sigma square B, and that is going to be the sum of x from 0 to 4, and we will have x minus mu, so x minus 2, since mu equals 2, square times f of x for each value of x. So we will go through and it'll be 0 minus 2 square times 0.2 plus 1 minus 2 square times 0.1 plus 2 minus 2 square times 0.3 and so on. And we get to a sigma square of B is equal to 1.6. Even though company A and company B means are the same, the variances are 0.6 and 1.6, so clearly company B has a much larger variance than A. Let's look at the alternative formula for variance. The variance of a random variable x, we have sigma squared, is equal to the expected value of x squared minus mu squared. So we're going to take a look at an example. The weekly demand for a drinking water product in thousands of liters from a local chain of efficiency stores is a continuous random variable x having the probability density function f of x of 2 times x minus 1 when x is between 1 and 2 and 0 everywhere else. So we want to find the mean and variance of x, so mu and sigma square. So we're going to start with finding mu is equal to the expected value of x. Now this is a continuous, so we're going to need to integrate. So we're going to integrate 2 times x minus 1, and we have to multiply by x. So I'll have x times 2 times x minus 1, that's the f of x, dx, with x from 1 to 2. And when we do this, integration, this will equal to 5/3. So our mu, or expected value of x, is 5/3. So now we need to find, to compute our formula for sigma squared, our expected value of x squared. So the next thing we're going to do is do the expected value of x squared. So we will do the same, we will do the integration, but this time instead of x times f of x, it will be x squared times f of x. So we have x squared times 2 times x minus 1, and we are integrating. So it's dx, and x is going to go from 1 to 2. And when we do this math, we end up with 17 divided by 6, or 17/6, for the expected value of x squared. So we're now going to take these two values, the mu and the expected value of x squared, and plug it into the variance formula. So this will equal 17.6 minus, we're now going to minus mu, so that's our mu squared. And when we do this, sigma squared will equal 1/18. So at this point, the standard deviation, or the variance, has meaning only when we compare two or more distributions that have the same units of measurement. Therefore, we could compare the variances of the distributions of contents measured in liters or bottles of orange juice from two companies, and the larger value would indicate the company whose product was more variable or less uniform. It's not meaningful to compare variances with different measurements, such as the distribution of heights to the variance of a distribution of aptitude scores. That would not be a good comparison.